So I would like to request Dr. Ganga Ram, please share slide and please address the participants. Sir, please unmute yourself.
Hello, can you hear me?
Yes, sir.
Okay. First of all, I would like to thanks Dr. Manoj Sahni, Dr. Y Cheng, and Dr. Neelam Singha for a very nice organization of this webinar. And also, I would like to thanks for the participants which are taking part in this beautiful events. So I am sharing my slides first here. Okay, so basically my topic is basic of fractional calculus and some applications. In this talk, the content of this talk will be the introduction, some applications of fractional calculus, existence, results of fractional order differential equations, some models, and finally will be the bibliography of the contents. Now, as you know very well, if we take any exponent of an integer, when we can easily calculate the values of like to the power 3, 3 to power 3, 4 to the power 3, a to the power 5, or a to the power 20. Just multiply number of times, means 2 times. If you want to calculate to the power 3, just you can multiply it 2 times, 2 cross 2 cross 2, and easily calculate. But if you want to calculate the value of to the power 0.3, then which procedure you can apply? Or if you want to calculate the value of 3 to the power 3.1, 4 to the power 1.5, a to the power 5.8, or a to the power of pi, then it is very complicated, but these value will be very applicable in many things. So basically, fractional calculus is also lie between the, because here the power will be the integer in this case, but in this case the power exponent of the any integer will be the any number. It may be rational, it may be irrational, or it may be fractional. So now suppose I consider the integer or derivative. You also know what is about the derivative of this. This is the first order derivative, dy upon dx, and this is third order derivative, fourth order derivative. This is 10th order derivative, and these derivative can be easily calculated if the y basically it is a function which is given smooth function, or we can say it is a differentiable function, and you can easily calculate the first order derivative, third order derivative, fourth order derivative. Obviously the 10th order derivative of a function is given. But suppose if you want to calculate the derivative like 0.3 order derivative, 3.4 order derivative, obviously the pith order derivative of a function y, then it is very complicated. But the fractional derivative has many applications in the distinct many fields in science and engineering. So basically we will emphasize on this type of a derivative. That derivative will be also called the fractional order derivatives. Not only the fractional derivative, it is also the fractional order integral. So origin of the fractional calculus, as Professor Y Chen mentioned in his slide, that the integer order derivative was started in 16, 19, 5 by using the nth order derivative of a function y, which is know everyone. But MDL Hospital raised the question on 5, means when, what will be the value of this derivative, what happened when n is 1 by 2. Okay, so basically this was the origin, this was the concept from that theory, from that day the fractional calculus was arise. So after that on date 30 December 1695, Leibniz replied to the hospital by this is an apparent paradox from which one day useful consequence will be drawn. Okay, and mathematically he defined that symbols by d to the power 1 by 2 y is equal to y square root of dy of such that y, like this way. Okay, so basically this was the starting of fractional derivative. So here is a list of mathematicians which have contributed their work into the fractional calculus. In 1736, Euler mentioned the integer order of a derivative by using the gamma function. In 1812, Laplace defined the fractional derivative by means of an integral. In 1822, Fourier gave the first step to generalization of the notation of differentiation of arbitrary function. In 1823, Abels considered the integral representation of arbitrary order alpha. In 1847, Riemann and Leverrier defined a fractional integral in form of the convolution type. In 1867, Gronal and Latner give the definition of fractional derivative of a function based on the finite difference method. In 1892, Hadamard defined a fractional integral and derivative in terms of the logarithmic function. In 1940, Ederle-Kobler defined a fractional order integral and derivative with the help of Malin transformation. In 1949, Rice gave the fractional integral and derivative of a function using the fractional power of Laplace operator in the multidimensional space. And in 1967, Caputo defined a fractional derivative of a differentiable function. In 1993, Miller and Rhodes used the fractional differential operator in the form of sequential term. And in 2000, Hilfer generalized the Riemann-Leverrier fractional derivative operator for Riemann-Leverrier and Caputo derivatives. Okay, so basically Hilfer derivative is the generalization of the Riemann and Caputos. Okay, and in 2014, R. Khalil and et al. Defined the conformal fractional differential and integral operator. Okay, so basically these are the some mathematicians who contribute their work in the fractional calculus. Some useful functions, the Laplace function, or we can say the Laplace transformation L of a function f is defined by equation 8, and inverse of this Laplace transformation is given by 19. Euler gamma function, basically Euler gamma function is a function which can be used to generalize the integer function to non-integer function. Okay, for this formula we can reduce that like this way. And also the Mittag-Levelov function, basically Mittag-Levelov function is also the generalization function of the exponential function. Okay, exponential function, hyperbolic function, sine quotient, these are the particular case of ML Mittag-Levelov function. Now, fundamental of the fractional calculus. The basic idea behind the fractional calculus is intimately related to the standard result of classical calculus. Basically, classical calculus from the fundamental calculus, fundamental theorem of the classical calculus. And also we know that means I am going the brief introduction about that. Suppose f is a continuous function and capital F is function which is defined by equation 18. Okay, so basically capital F is equal to a to the power a fx dt, and basically it can be represented by the j. Basically it is the integral representation of a function ft. Okay, then f is differentiable and df is equal to ft. You can write equation. So basically this is the fundamental theorem of the classical calculus. Here f is defined like this way. F is here continuous function, and you can take the differentiable of that function and just you can obtain the previous function, that one. So means df is equal to small f. Now we can generalize this concept. We have the following result. Means d for derivative of integral will be equal to the previous function ft. Derivative of the integral of a f ft will be the function f. Now if we can generalize, which implies that if we take the nth power of that, means n power of derivative of n order of integral of ft will be ft for any integer. Here this is the one order type, but we know from n-fold integral, means Cauchy integral formula, from the complex analysis you can easily know that means n-fold integral will be represented by this formula. So 1 upon n minus factorial a to the power tt minus n minus 1 f of ds. Okay, so we can derive this formula by just using the taking the function as a continuous function and integrable. Then basically this is equal to this, means jar integral of ft will be equal to just a to the a is the lower limit, t is the upper limit of f dx, and just we can take the twofold integral, and basically twofold integral of ft will be equal to a to the power t t minus f s ds. So and if we again we take the threefold integral, then I will obtain this one. Okay, so we can continue this process. In general case, n-fold or Cauchy formula will be like this way. Okay, means that it will be the it is a Cauchy formula. Okay, now replacing the integer n here it is given here, this is n integer order derivative. Now replacing the n by a real number alpha and taking a lower limit as a 0 in the Cauchy integral formula, so we can obtain the Riemann-Leibniz fractional integral operator, and that operator can be defined like this way. So basically Riemann-Leibniz fractional integral operator is defined by equation 21. Basically it is n, from where it come, this come from the gamma function. I have told you that by this one. Okay, this one. So basically equation 21 represents the Riemann-Leibniz fractional integral operator for a function ft. So in this case the function on, now let n be any positive integer which is lie between n minus 1 to n. Then by noting that, so basically this is the basic result of classical calculus, and we can define like this way: d to the power alpha ft is equal to d to the power n j to the power n minus alpha ft, namely. Okay, and basically this is a particular name of that derivative that will be called the Riemann-Leibniz fractional derivative. Equation number 21 will be represent the Riemann-Leibniz fractional integral, but equation 22 represent give the definition of the Riemann-Leibniz fractional derivative. Okay, now just by changing some notation into this previous notation, we can define the capital fractional derivative. So this equation 23 represent the capital fractional derivatives. Okay, so these are the fractional derivatives. Okay, and also some authors use the generalization of the capital fractional derivative, that will be the classical capital derivatives and generalized capital derivatives. Okay, also Hadamard fractional derivative is defined by equation 23, Hadamard fractional integral operator, and Hadamard fractional derivative of a function f is defined. You can use 25. Grana-Latnikov fractional derivative of a function is we can define is defined by equation 23. Okay, and others many type of the fractional derivative and integral also exist in the fractional calculus. They are Hilbert, conformal, Valley, Kobler, Markov, Rice, and there are a lot of fractional derivative because there is no stability of the fractional derivative and fractional integral yet. According to the applications, different type of mathematicians can use the different type of fractional derivative and fractional integral operator according to your suitable way. Okay, now some example. Suppose we have a constant function fxt equal to c. This is a constant function. Then the Riemann level of fractional derivative of a constant function will be this. But in the case of a ordinary derivative, the derivative of a constant function must be zero. But in this case, in the sense of Riemann level of derivative, the of constant for the constant function is not equal to zero. Okay, and but in the sense of the capital derivative of a constant function must be zero, because due to in the definition of capital and Riemann value there is a difference that the function in the capital sense the function must be differentiable, but in the Riemann sense there is no need to the function may be differentiable. It may be only continuous case. Okay, so this is the major difference between the Riemann value of fractional derivatives and Riemann capital derivatives. Suppose we have a power function and we can easily find the Riemann level of derivative of the power function like this way. Okay, and capital derivative of power function is the same, like 32. Okay, and Riemann level integer of a power function is given by 33. Equation number 33. Let us consider the exponential function. Okay, and Riemann level of fractional integral of a exponential function will be the in terms of the ML function, and Riemann level of derivative of exponential function also will be the in terms of the ML function, Mittag-Leffler function, and it is the capital derivative of exponential functions. Okay, and non-Latnikov exponential function is defined by equation number 8. Okay, now if you take the trigonometrical function of sine 10 cos t, then Riemann level capital Gronal integer derivatives and integral can be calculated by easily, because using the definition of a sine and cosine function in terms of the exponential functions. Okay, now if we know the derivative of exponential function of, then just you put the value of these exponential of, then you can calculate the value of derivative of sine cosine in terms of the Riemann capital Gronal etc. Now some applications. Consider harmonic oscillator motion. So basically this is a basic motion in the oscillations theory, and also you know about the terms of this differential equation. Basically m represent the mass of a bob, and mu dy upon dt basically represent the damping force, and gt is the external force, and the kyt represent the Hook law. Okay, so basically this is the equation 43 represent the harmonic oscillator motion. Okay, and we can take the particular case of this problem without taking the friction force and external force. Means if we put here, if we take the damping force is 0, and also we can take the external force gt is 0 here, then the equation can be convert into the this form. Basically this is the particular form when there is no friction force or external force on the system, and just we can take omega square equal to k upon n. Okay, basically this is the constant. Okay, and now from the theory of ordinary differential calculus, with taking the initial condition, the solution will be of this, just yt equal to y naught cos omega t. Okay, and the graph of that solution, basically this is the solution of the particular case of that harmonic oscillation motion. The graph will be only oscillations type, because amplitude will be the same in whole the period. Amplitude must be the same whole the period. Okay, but so this one is the ordinary case. Suppose we want to replace this ordinary case into the fractional case. In general, taking alpha in place of order 2. So in general, harmonic oscillators motion model involves the friction, because when we take the bob in the atmosphere, then it for some time it will come to the rest position, and this friction will leads to the decrease in the rate of the variation of space time. Okay, so so we can consequence that integer order derivative equation can be taken as the fractional order derivatives, and same conditions we can take for this system initial conditions, and the solution of equation will be in the form of ml function. Yt will be y naught alpha naught omega to the power alpha t alpha for omega 1 and y naught equal to 1. So basically this is the solution of our problem. Okay, now if we draw the graph of that diagram will be represented by this. So from this diagram you can see that when alpha can be decreased, the oscillations of the bomb can be decreased, and when alpha 10 goes to the order of 2, then the oscillation can be constant, means the amplitude may be constant, same position. Okay, so basically this example show the beauty of the fractional derivatives. So basically fractional derivative give the natural behavior of the systems. Fractional derivative give the natural behavior of the systems, but integer order derivative does not give the natural behavior of the systems, dynamical system like that, for a dynamical system. Okay, others applications of fractional calculus in mechanicals, you can see that as Professor Y Chen discussed that the fractional calculus can be used into the mechanicals when we calculate the viscoelasticity of intermediate liquids, means solid and liquid. And also you know that the relation between the stress and strain, it is equal to the Hooke law for the solid and Newton's law for the fluid. So basically this is the relation between the stress and the strains. Okay, so this relation 46 give the for the solid materials, and the relations Newton's law give the for fluid relations. But there are many types of materials which lie between solid and liquid. Okay, for yeah, or we can say that for the intermediate materials stress, the Scott Blair first give the representation between the stress between the solid and liquid, and he can use the he used the order k in place of 1 and 0. Okay, so it means that to find the stress between the solid and liquid means to find the stress between the intermediate position of a liquid and solid, we can use the fractional derivative. This is a very nice application of the fractional calculus. And basically this relation is called the netting law for viscosity materials. Second one, second application is found in the classical mechanics. Basically, to find the pattern of the fractionless plane curve with homogeneity gravity field in the xy plane, we can use the integral equation. Basically, this is the integral equations, and that equation basically represents the Abel's integral equation. And this Abel's integral equation is nothing. Basically, it is a fractional order differential equation. Okay, it means that to find the pattern of the fractionless plane, we can use the fractional calculus. Okay, this is another application of the fractional calculus. Okay, and this equation basically is called the totocron problems. And control engineering, you know very well about the control. Professor Pritham and Professor Y Cheng also discussed more detail about the control theory. Okay, so there is no need to explain more about that application, the theory of fractional calculus. Okay, electrochemical we can use the fractional calculus, as we know that the relation between the current it and charge qt near the electrode surface can be represented by the relation means qt means q is charge d to the power minus 1 it current. Okay, this approach, basically this approach does not involve any assumptions about the kinetics of electric process, because we are when we calculate the current and we give the relation between the current and charge near the electrode surface. Okay, so this relation does not give any information about the kinetic of the electrode process, property of the electrode surface at all. Okay, so to give the information about the electrode process, kinetic of the electrode process and property of the electrode surface in place of integer, basically this is nothing, it is the integer order integral equation. Okay, so we can use the fractional order differential equation. Okay, oh, it means that the concentration of the electric characteristic between the IT and QT to determine the concentration of analyzed electric species near the electrode surface. So it is very useful to find the fractional calculus. It is very important. Means we can use the fractional calculus in place of the integer order derivative. Okay. Electromagnetic. It is well known that the axial multipole exponential of the electrostatic potential of the electric charge distribution in 3 dimensions is given by here. Okay, so basically Pn represents the ordinary derivative of order n. Okay, but ethanol realized that the idea of the integer order multipole using the fractional derivative. Okay, so this is another application of fractional calculus. Fluid mechanics, the classical advection dispenser equation represented by equation 58. Okay, basically this equation represent describe the propagation of the pressure a small particle fluid and follow the Fick law, this equation. But when the fluid pass through the small tracker vortices, small regions, okay, that equation does not work here. In that situation, that ordinary derivative does not work here. So to handle of such problems, to handle such situations, we can use the fractional derivatives in place of integer order derivative. Here, this is the second order derivative. Okay, when we use the fractional order derivative, then we can handle that situations when the fluid flow into the small regions. Okay, so this is the another nice application of the fractional calculus, which is found in the classical mechanics. Electrical engineering. Also in the circuit, the process of discharging of the battery may be described by simple equation. Simple equation, basically d upon dt is equal to this upon 1 upon rc. These are the constant minus 1 upon rc. Resistance and capacitance and qt is the charge. Okay, so basically this is the relation. Just simple relation means this is the process of discharging of the battery. Okay, but this process does not give any information about the number of charge cycle or age of the battery. Okay, so what can we do? So we can replace, if we replace the integer order derivative to the fractional order derivative, if we replace this integer order derivative to the fractional order derivative, then we can handle this problem. Means to describe the behavior of the discharge battery. Okay, to describe the behavior of the discharge battery, the fractional derivative will be the applicable. So this is the very other application of fractional calculus in electric engineering. Biomedical science, we can use the fractional calculus in the biomedical science. In the body, when you drug rapidly distributed within the tissue, then the rate of loss of drug described by this equation. Okay, so basically in the biomedical, when in a body, when drug rapidly distributed within the tissue, then the rate of loss of drug is described by this integer order model. Basically d upon dt is the integer order model derivative, where cpt is the concentration of the drug after injection, cl is the rate constant of the drug. Okay, but so when will be this model not use? To study the changing drug concentration, we need to collect the large number of plasma. To study the changing drug concentration, we need to collect large number of plasma samples to see how the change happens. Okay, however, taking the large number of sample from the patient is very difficult. So from this, if we take this model, this is very dangerous for the patient. Okay, so what will we do? So if we take the small number of sample and we can use the fractional derivative in place of integer derivative, then we can study the changing of drug concentration of the patient. As a consequence, following model will be used to study the drug concentration. Okay, just in place means replacing the order of that differential equation. So this is the another application of the fractional calculus in biomedical. Okay, and basically this relation is called the pharmacokinetics models. Operation research, also you can use the theory fractional calculus in the operation research, where when we use the fractional calculus, the classical EOQ theory inventory model, basically represented by the equation 1644, where D denotes the demand, where D is the demand rate and QT is the stock level. Okay, so what are the condition? This model, what are the condition? This model does not have give the full information about the classical theory quantity. So it is naturally seen that the demand rate, basically this demand rate varies high or low according to the market situation. So when it means that in this situation, when the demand rate vary high or low according to market situation, that model does not work. This integer model does not work. So just we can replace the integer order derivative to the fractional order derivative. This then we can handle this demand rate. Okay, this demand rate can be described the following model. So this is another direct application of the fractional calculus in the operation research. Image processing. Also, we can use the fractional calculus in the image processing, as Professor Y. Cheng introduced the application of fractional calculus in image processing. Okay, and you can see that the moving window coefficient matrix basically W, that can be used to smooth the signal. Signal means basically it is image to estimate the eye point of the filtering of window. Okay, the above equation work well when used for high frequency features of the image. Okay, basically M here, W is the window matrix. Okay, so basically this equation work well when we use the high frequency features of the image. Nevertheless, their performance go down significantly when applied a smooth region. Okay, so when we applied a smooth region, that model does not work. So what will we do? So we can use the fractional calculus. If we use the fractional calculus, fractional window matrix, then we can handle this situation. Okay, civil engineering, the problem of longitudinal variations of the harmonic external force beam can be used fractional calculus. In the statistical engineering, fitting of the experimental data, biochemical modeling of polymers and proteins, and lot of applications of fractional calculus in the found in the modeling of human tissue under the mechanical loads, impedance of the fluctuance, rheological force media, dynamics of earthquake, kinetics, dynamics, and neutron networks. Okay, these are the other application of the fractional calculus which can be found in the realistic words problems. So these are the some journals of fractional calculus. The first journal is the progress in the fractional differentiation and applications, which is from the USA. Second one is the fractional differential calculus, Croton Ditya. Classic Journal of Fractional Calculus and Applications, ZIP, and Fractional Calculus and Applications by Bulgaria. Okay, so these are the very reputed journal of fractional calculus, basically core journal of the fractional calculus. Okay, now these are the references books. These are the references basic books in which the theory of fractional calculus is given and some applications also given into the references book. Now some existence result of differential equations. Basically, consider following equations for 68, 69, and 70. So basically these are the differential equations. First two these are the ordinary differential equations, and third one is the fractional differential equations. Equations 68 and 69 basically have maybe some, as you can see that this equation has homogeneous means trivial solution, may have a non-trivial solution, and may have a unique solution. Basically these equations may have some solutions, may not solution, and unique solutions. So what will you do? So basically our work is, now I am coming to my research work, existence of fractional order differential equations, existence of solution of some fractional order differential equation. Okay, so mathematical formulation of the fractional order differential equation. So to convert a differential equation into the integral equation, we can use the theory of fixed point. We can use the theory of fixed point, means functional analysis we can use. For this purpose, we consider a Banach space X and a non-empty closed convex space C, and we will define a nonlinear mapping T here. Means the fixed point of the problem means nonlinear mapping T can be defined like this way: I minus Ty equal to 0. Basically, this is nothing, it is a fixed point problem. Okay, we use to denote the set of fixed point by fixed T, and basically it is nothing. Y belongs to C. C is a non-empty closed convex subset of X. X is here Banach space. Ty equal to X. For example, if we take X square X, X square X, suppose if we take X square X, then the fixed point of this equation will be 0 and 1. Okay, basically fixed point theory has three aspects. In the fixed point theory, there are following fundamental aspects in the fixed point modeling. First, existence of the fixed point, uniqueness of the fixed point, and computation of the fixed point. Okay, so basically these three aspects depend on the model operator T C2X, where C domain and X is the range of the space, Banach space X. Now consider a simple fractional order differential equation of order lie between 0 and 1 with initial condition taking the capital fractional derivatives, and the operational interval is given here 0 to 1, and basically this is a, we can take the general equation, general fractional differential equation with initial condition, and in this case I have taken the capital fractional derivative. Okay, with respect to this equation we have the following questions. So under what condition the system 73 to 74 admit a solution? Under what condition? Under what condition this system has a solution? If the solution exists, is it unique? If there is a solution, then for what value of t, means what is the operational interval for this solution? So basically we have three aspects when we discuss the existence of the solution. Existence of the solution means consistence of the solution, means actually that solution exists or not. Consistent of the solution means it has a solution. It has a solution, it may be unique solution and it may be infinite solution. Okay, one solution or more than one solution. Consistent means that system 73 to 74 is consistent or inconsistent. Okay, so basically, so what will you do? So first of all, we will achieve our goal by converting this system into the integral equation. Okay, why we convert the differential equation into integral equation? Because the integral operator have very many good quality in place of the integer order derivatives. Because boundedness, compactness, etc. all are very easily can be defined in the operator, integral operator equations. So we can convert this fractional fractional differential equation into the integral equations. Okay, now we can use how can you convert this integral equation with the given differential equation? Just there are, we can use two methods. First one, we can use the direct integration method, and second also you can use the Laplace transformation, and both I have already discussed. Okay, so basically I have simple equations and we will convert this equation into the integral equation. So I want to discuss my problem, this one. So basically this is very generalized problem. In this problem, this is a fractional differential equation, and basically q basically represent the neutral, and f is a function of t x rho t x t bt dt. So basically x rho t is called the delay differential equation, and also equation 78 represent the impulsive condition. So this is a impulsive fractional order neutral differential equations, okay, which is found in many areas. So basically what will you do? So we can apply the theory of we can apply the fixed point theorem of this problem, and we can check if that equation has a solution or not. If the solution has, then what are the conditions for these solutions? What are the assumptions? What are the assumptions of this model? That system has a solution. So I will not go. I will not go to the detail of this equation. Basically, this equation can be converted into the integral equation. Integral equation, and converting this integral equation, we can take some assumptions. Under some assumptions, this problem has a solution. Basically this, we can use the fractional Banach fixed point theorem or other fixed point theorem to check the existence of the solution of the problem. Okay, so I will not go into the detail of this. I skip all these. Okay, so I want to tell you some models. The model of the fractional calculation with initial boundary non-local and impulsive effects can be used by inclusion problems. So fractional calculus can be used into the inclusion problems, can be evaluations problems, can be used control problems, and also stochastic problems. Okay, and also fractional calculus can be used into the graph theory, also engineering problems. So these are the references, and thank you. You are welcome.